let's see. Let's see. All right. All right. So, looks like we're live. Okay. So, welcome back to another stream. So today we're going to be doing something a little different. We're going to, well, a little different, a lot different, in fact. Today we're going to be starting a new project. So, per the results of the poll from a few days ago, or a few weeks ago, I guess, we're going to be developing a robot from, we're going to go back to robotics, and we're going to be developing a robot from scratch that is intended to be used with the robot operating system environment, and more specifically with the nav2 environment. So the goal here is that we're going to build effectively the simplest robot that we can that's fully compatible with a simultaneous location and mapping system, which, as the name states, the core, the core function of this being, you have a robot, doesn't know where it is, it doesn't know what the environment it's in looks like, so it has to simultaneously figure out where it is and what where it is looks like, and then in the future, preferably, save these maps that it's creating and navigating them in the future, storing changes, things like that. So we're going to be So what is robot operating system? So robot operating system, and specifically robot operating system 2, because robotics operating system 1 is gone, but the whole point is that it is a standardized framework that defines how robots are constructed. The idea is that if you can generalize a robot to basically generalize the robot's behavior from the robot's the implementation of how all of the hardware with the robot works, that you can reuse all of the robotic software that you developed to control a robot, and all you'd have to do is develop a hardware, essentially if ROS2 is so why no ROS3? Because there are plenty of versions of ROS2. There are new versions of ROS2. We're up on ROS2K, which means there's well over 10 versions, and there's one version here, right? So So standardized platform for writing software for robotics. The general idea is that you have the core part of ROS is something called a data distribution service, which is a fancy name of saying a publisher-subscriber net system, where you have multiple programs running on the robot, and they can offer data and services that can be called from other software running on the robot. And the idea is that you would have a generalized interface that is defined on a separation between the software the robot's running and the hardware of the robot. So you would take the standard set of services and data that would be published by the hardware stack of the robot, or of a standardized interface, and as long as your custom robot implements a service that provides those actions and those hardware interfaces, any software written for that robot should work. So again, today what we're going to be trying to do is developing the most simple robot possible that's fully compatible with this. So what does that mean? So nav2 is the framework that we're mostly going to be trying to run, and one of the core parts of nav2 again is this idea called SLAM, or simultaneous location and mapping. And as the name states, it's for both mapping, it's for localizing yourself with a map, and if you don't know where you are, it is also for building a map. So what do you actually need to do this? So for the most part, the robot needs sensors to measure the environment around it. It needs the ability to measure how it's moving. It needs the ability to measure logic and control can be ported to other robots provided the hardware and correct. So for the most part, the most basic robot that you can build with this, you need a way to measure the environment around you. You need a way to measure your own movement in that environment. So this realistically boils down to pretty much having a LiDAR. Actually, it's not explicitly required, but you need a high precision sensor to measure the environment around you, whether that is a full like 360-degree LiDAR or like a depth camera, like something like a Kinect, or related sensors like the Intel RealSense, or actually it's not actually Intel RealSense anymore. They sold RealSense. They spun RealSense off. They didn't sell RealSense, which is funny because they bought RealSense a number of years ago. But anyway, or Luxonis OAK-Ds, or any number of other sensors. So you can use either a depth camera that's producing a point cloud. You can use a LiDAR, some sensor that will give you a lot of data points that measure the environment around you. Also, you typically need in your chassis, you need odometry, which is the idea of being able to measure how you're moving. So any moving component of the robot base, you would put a sensor to measure how it's moving. So an encoder, motors would have encoders on them, so you can measure the rotation of the motors. You also typically want some type of inertial measurement unit, but you don't necessarily need a compass, but at least a 6-axis, at least 3-axis accelerometer, 3-axis gyroscope. The other sensors will compensate for not knowing their exact heading, and honestly, magnetometers are tricky to use inside, because there's all sorts of wires running through your house, and you might turn on the vacuum cleaner, and all of a sudden your compass needle points to the other room, So anyway, yes. So we're going to be trying to build this very simple robot based on, I don't want to say very simple. It's actually by Arduino robotic standards, they're quite complicated. But so let's actually at least sit down and put a list of requirements of what we actually are trying to use here. So we're going. So I like to use this tool called Excalidraw. Excalidraw. I'm spelling this. There we go. Makes these nice, pretty little hand. Oh, this is from a YouTube video I did before. Oh, I'll delete that. So we'll zoom in. We'll turn on the grid. Toggle grid. Yeah. So what we're gonna do is we're going to build. Oh, I need text tool. We'll just go black text. So we're going to build a robot based on a robot plan called a differential drive robot, which is basically just a robot with 2 wheels and a motor driving each wheel. The robot goes, if both motors go forward, the robot goes forward. If both motors go backwards, the robot goes backwards. If the motors spin in opposite directions, the robot spins in place. Generally. Basically, the turning is the difference between the motion of the 2 motors. Differential drive. So fairly straightforward robot platform, or designed for a robot base. Everybody's beginner robots are always differential. I mean, there's lots of differential drive robots out there. But anyway, so we're going to go with a differential drive chassis. We're going to have a LiDAR. So in terms of sensors, we absolutely need a LiDAR. We need an IMU, and in this case, we're going to reuse one of those MP6050s we used for the balancer robot stream in the past. So 6050, we need wheel encoders, and these can be built into our motors. So we need wheel encoder, or at least encoders on drive motors. Encoders, and as far as compute, we're going to go with a Raspberry Pi 5. And Pi 5 for the main compute, and then we're going to go with a Raspberry Pi Pico 2 for the this can be running Linux, or running ROS2 under Ubuntu, and that might be a little be Ubuntu 2404. It might be a little strange if you're used to running Raspbian on your Raspberry Pis, but ROS historically has only ever really been supported running on Ubuntu. And now it technically has platform support for other operating systems. Like, you can run it on other Linuxes, you can, or Linux distros. You can run it on Windows in theory. Doesn't run very well, but you can at least run some of the visualization tools on Windows. It is supposed to work, but it definitely doesn't work as well as it does running under Linux. So we'll run ROS2, which is a software stack, mostly, even though it's called Robot Operating System. It's mainly software stack. That'll run on top of an actual operating system, so we'll just kiss Ubuntu. It is far easier to run it under Ubuntu on a Raspberry Pi than it is to run it under Raspbian on a Raspberry Pi. And then we're going to use a Pico 2 to control all of the actual low-level hardware. So this will drive the LiDAR, the motors, read the encoders, read IMU, etc. And the differential drive chassis, we're actually, to save ourselves a little bit of time, we're going to go with an off-the-shelf differential drive chassis. And because one of the themes of this channel, anyway, is to... Yeah, that would be a very masochist move. Running ROS on Windows Server 08. I don't know if you can run it on 08. Like, you might... Well, again, you'd be in pain. So we're going to take a... So as one of the themes of this channel is to try to help me focus on projects that I have forgotten about, or put on the back burner. You know, one of the goals here is finally finishing all that stuff I started, right? We're going to go with a chassis that I'm almost certain none of you have ever heard of. And we're going to go with a chassis called the Robotics Connection Stinger. Which is just a two-wheel drive, you know, differential chassis. And so these are the story on this. Jeez, my uncle. So in terms of just how on the back burner doing anything with this chassis is, I received this chassis as a Christmas gift from my uncle in 2007, I think. Yes, Christmas 2007. And so I've had this thing bouncing around my closet for just about 18 years. So now that's not to say I haven't built anything on it before. I did a little project on it that I called... I don't even remember what I called. I can't even remember what the first one was called. But I did this... If you've seen my Bare Metal 386 series, or at least the one that I never finished, you know, if you've at least seen the title card or something from that, you see the old DOS 386 PC-104 computer. Well, pictures, robots, old bots. Yeah, so I built a robot on this chassis using one of those really old DOS computers, and I thought this would be funny. Or actually, I mean, realistically, I thought it. I didn't realize that the processor that it fully grasped in, you know, my teenage years, that the processor in this single board computer was not that much faster than the AVR that's in that board that handles all the hardware control. Like, anyway, so it did have a heck of a lot more RAM. Well, we'll give it that. But in terms of actual raw compute, it's not that much faster. Ironically, the AVR has more memory bandwidth. Which is saying something. Anyway, but yes, so it's going to be this chassis, which I have kept around all of these years. And so, let's see. So we're going to do, so let's actually go take a look at this chassis. So I'm going to turn on the desk camera here, which, you know, the desk cam, you know, the phone running, you know, take my fingerprints out of the camera lens here. Let's switch to the camera and go take a look at this chassis. All right, so, you know, as all good things, you know, it's just stuck on the shelf. So we're going to take all of whatever the heck this stuff is, and we're going to, oh, there we go, there's a line bar. And, oh, what's in there? I don't even know. Okay, that's motor controller. So, so here is our Stinger robot chassis from so many years ago. I'm gonna put that down here. I'm gonna spin. While I mount the camera, I'm gonna spin this back over to my desktop. I'll take the case off here. Alrighty, turn the light on. Perfect. Okay, desk cam. I minimized droid cam. Oops, droid cam. There we go. Alright, so hopefully... There we go. Alright, so push that out of the way. So the Stinger, it is a differential drive chassis, which means that you have two wheel. If we hold it the right way up, it kind of looks like this. It's just a giant triangle. There are two motors in the front with these like foam wheels that used to be popular, decade before last. So yeah, differential drive, it's two wheels, two motors. They spin, independently. There's a tail caster. So if we put it down, pretty much just can drive around. If you turn them in opposite directions, the robot spins, so on and so forth. Nice little satisfying switch. All right, and for the LiDAR, continuing with the theme of using old stuff, we are going to... there are, again, I'm using this because, not because it's good, but because I have it, and if I don't use it on this, I don't know where, if ever, I'm going to use it on something. So, this is a Nito XV11 LiDAR, or I should say it is a LiDAR from a Nito XV11 robotic vacuum cleaner. I bought this back in 2013, 2012, 2013. If anybody remembers the Nito XV11 vacuum, everybody's pretty used to robot vacuums having LiDARs in them these days, but back in the early 2010s, it was a really unique feature. Like Roombas, for the most part, would just meander around, and statistically, you could say that after a certain amount of meandering around, it would have covered every part of your floor. But if anyway, sorry. So Roombas, they didn't have a particularly sorry. I'm getting ahead of myself again. So yeah, LiDARs and robotic vacuums. So the because these kinds of sensors were really expensive, lead up until only in the last couple of years, let's be perfectly honest. It's really all of this like robotic car autonomy stuff that's really brought the cost of LiDARs down. Anyway, so in 2008-ish, eventually concurrent map extrusion. Yeah. So yeah, if you look back at like 2008 or when late 2000s anyway, Roomba came out, robotic vacuum, nice. It would could pick up breadcrumbs, but it would drive around and eventually it would vacuum your room because statistically you could say if every time you hit something you turned a random amount, you could statistically say that eventually you'll cover all of the floor space. But the problem was, in order to actually do that in any good length of time, or any reasonable amount of time, the robot had to be able to run for a while, and the only way to have something like a vacuum cleaner running long enough on the batteries that were available at the time for a while was to use a relatively weak vacuum. So they weren't really that good at vacuuming anyway. So Nito was a company that came up. They created effectively at the time like the world's cheapest LiDAR, which is what this is. Now, before this came out, I believe the cheapest LiDAR that, at least in single unit prices, that you could purchase was a Hikoyu. I can't remember the part. I mean, the part number doesn't really matter, but it was similar feature set. Only worked inside. Could measure a couple of 100 points in the circle around it. Could see out to 5-6 meters. There's this unit by a company called Hikoyu, which is still around. They make good LiDARs, but at the time it was like $1,200 in 2010, I think. And so for a vacuum that you're trying to sell for $400 retail, obviously you can see the problem. But Nito was like, wait a second, if the problem with these robotic vacuum cleaners is that, one, they just suck. Well, they don't suck. They suck because they don't suck stuff up very well, right? They're like, well, we need a more powerful vacuum in a robot, but the problem is we don't have the battery power, we don't have the battery life to run the robot for that long. Because at the time we were still kind of concerned about sticking lithium batteries in consumer products. Like laptops had them, but it was kind of because what else would they have? So a lot of the like early Roombas and even a lot of the early Nito vacuums, they had nickel metal hydride batteries, so you really only had so much life in them. The energy density wasn't fantastic, but so either way, the problem is we want to run a more powerful vacuum because we actually want the robot to be useful. But the problem is, because we have a big vacuum, it can't run as long, so we need to be able to vacuum the room quicker. So we actually need to know where in the room we are, so we can, only cover every spot once, so that we know we vacuumed it. And so their solution was, well, the only real way to know where you are at the time was a LiDAR, because you don't have to augment your environment to use a LiDAR. And LiDAR technology, at least at the time, was far further along and still is better than alternative approaches, because I think current Roombas, what they do, they use something called optical flow, which rather than something like a LiDAR measuring points, they actually have a camera pointed at the ceiling. And they actually run the same types of algorithms on those sensors that you would run in, a wireless mouse. And the problem is that because of, you need visual features to track, they don't really work well unless your ceiling has some kind of texture on it. So if you have a flat white ceiling, those optical flow sensors really don't work all that well. So the LiDARs are still the better approach. But anyway, so Neo realized they wanted to use a LiDAR, and nobody was going to buy a robot, or very few people. It was not going to be a consumer device if the LiDAR alone cost $1,200, because let's just say that, when you're building a hardware device, I don't, but in terms of going to retail, let's just say you can't, of the price tag that you see at the store, you realistically, in order to give your store some margin, to give yourself some profit margin, the hardware can't really cost more than half of the price tag you see. So, realistically. So, in order to, what do you call it? So $1,200 sensor in a robot that they wanted to sell for like $400, it's just not going to work, because it's basically probably saying that their bill of materials can't exceed $200 something. So they needed to build a LiDAR. They need to figure out how to make LiDARs cheaper. And so they developed what at the time was the world's cheapest LiDAR. And they did, I don't know what they actually did cost to produce, but I know that spares cost $80. In 2010, well, I bought this in 20. Well, this cost me $80 in 2013. So in 2013 dollars, this cost $80, which should probably put it at low 100, 110, 120 these days. So anyway, that's a long-winded explanation of this whole thing. But we're going to be using this XV11 LiDAR because, again, I bought it for, I intended to build exactly what we're building today, probably about 10 years ago, but I never finished it. And I don't, well, realistically, it's because I was in college and I had other things to do and I was playing a lot of video games. And trying to pass school. But either way, we're going to be doing that now. And computer-wise, we're in a lot better place than we were then. Back then, I believe, I was trying to build something that I called the BeagleBot. I don't know where I stuck this picture. It might be on my website. So I think I put a picture of it in my latest... Nope, I didn't put a picture of it. Actually, you know what? We're going to Google Beagle... Actually, you can't even see my... Okay, sorry. BeagleBot. I think there's a page... Oh yeah, on the BeagleBoard website. So this horrible picture is the only picture that I really ever took of it. So I was thinking, I'm gonna build a... Oops. Wow, they used Imager to host their... Interesting. Interesting. So they really used Imager to host their pictures. Okay. Anyway, BeagleBot. That was switched from using a DOS computer to using a BeagleBone, because in 2013, the BeagleBone was far nicer platform than the Raspberry Pi. The Raspberry Pi is very nice now. It wasn't always. I mean, the whole point of the Raspberry Pi was be really cheap. I mean, that was the original goal. What was give people an introduction to computing for a low price. So the original Raspberry Pi, I believe, the original A model, the target was $25. I believe it was supposed to be. It was a $25 computer. You remember it was supposed to be a $15 computer or $25 computer, but something like that. And then the B model actually had the I/O and the USB ports cost cost $10 more, $35 or $25. It's something I can't remember, but. Yeah, you can even see this was my goal back then. Connects and Nito LiDAR. Yeah, here we go. So I took the parts lying around the house and along with a replacement Nito LiDAR I found online and started building BeagleBot. And this was posted in 2014. It doesn't say in here, but I believe if you go to the Imager link, yeah, 2014. So we're talking over 10 years ago I was thinking of doing this, and I never did it because I'm by reasons. So anyway, we are starting to finish this project today. And so what we're going to do, all right, so we got that. Where am I going to write? Yeah, BeagleBoard. Anyway, 2013, the BeagleBone was a much better platform for robotic stuff than the Raspberry Pi. It was faster. It had more. It was faster. I mean, the Raspberry Pi was a 700. I mean, you can overclock the Raspberry Pi, but the original Raspberry Pi was like a 720 megahertz, 700 megahertz, ARM v6 class processor. I mean, it was still 32-bit, but it was old. I don't think it had a similar processor in it to the first iPhone, and then this effectively was an iPhone 4. So 2-3 hardware generations newer, realistically. But BeagleBone was good, but quickly the BeagleBone got surpassed by the Raspberry Pi eventually. So today we will be building with the Raspberry Pi 5, because realistically, after everything, the Raspberry Pi is in fact the I'm going to make a statement that I believe, but I mean, if people want to correct me if I'm wrong, but I do believe this to be true. I believe that the Raspberry Pi is at least the best supported Linux ARM single board computer on the market. There are others that have decent support, and I'll basically say nobody beats Raspberry Pi on the support. Like, it's great. Like, they are still shipping images for the first one that came out, in 2012, 2013. Like, they still ship 32-bit OS Raspberry Pi, 32-bit Raspberry Pi OS. You can still take a modern image, modern kernel, boot it on the original Pi. It doesn't go very fast, but at least it's still supported. It's not e-waste. I don't know what you're going to do with one, but the limit of your imagination, software will not be the wall to climb over, or the availability of an operating system is not a hurdle you have to climb. And then in tier 2, I would personally put the BeagleBoards, I would put the BeagleBone and the BeagleBone derivatives, because the original BeagleBoards are no longer supported anymore. But the BeagleBones, even this old BeagleBone White, this is the first generation BeagleBone. There's still images available for this thing. They still ship them. They don't ship this particular version, but they do ship the hardware, the software image for it. Anyway, but anyway, yeah. Tier 2, Texas Instruments, the BeagleBoard, most of the new BeagleBoards, good software support, and also the NVIDIA Tegra, the NVIDIA Jetson platforms, like the Jetson. I put that at tier 2. Personally, people might heavily disagree with me on that, but I put them at tier 2 only because, one, all of the driver work for it is proprietary. So once NVIDIA decides to stop supporting it, you're cooked. There is no, open. They're very realistically, once NVIDIA stops supporting a particular model of Jetson, like, that's it. Either pay them to keep supporting it for you, or you're done. You buy a new one. If you're in that market, you don't try to use old computers. But because there is no open community around it, the moment NVIDIA stops supporting it, it realistically becomes e-waste pretty quickly. So I'm just going to put it tier 2 because it's very well supported during its product cycle. But once the product cycle is over, get wrecked. Anywho, back to the desk cam. All right, so component. My phone went to sleep. Sorry. So component selection. So we've got ourselves a differential drive chassis. We've got ourselves a Nito XV11 LiDAR. We are going to use if I can find it. We're going to use. I'll be right back. Alrighty, I'm back. We are going to use a Raspberry Pi 5, which is in this nice case. You can pull open and see Raspberry Pi 5 in there. Not pulling your leg. It's a 5, not a 4. So we got Raspberry Pi 5. We're going to take the M.2 off of it. I might put the AI hat on it. I'm not sure. But we're going to take a. Oh, that's a Pico 1. We're going to use a Pico 2W. I also have Pico 1s. Pico 2s, no Wi-Fi, which will be what we eventually use. But until we get the Raspberry Pi software up, we'll just plug the Pico 2 in. We'll plug a 2W into it so we have some remote connection to it. We've got this 5 amp. AliExpress, so supposedly 5 volt, 5 amp voltage regulator. Scrap a proto board to work with. I got all the other stuff on my table over here. Any other big hardware choices? Let me go grab the battery. We'll do a back again. All right, so we're gonna do lithium battery. Another, I want to call this just a special low cost battery from an Alphabet brand off of Amazon, but they actually work. They match their claim specifications. So I can't complain. There is nothing to complain about. It says that it may be an Alphabet soup brand, but it says it holds this much energy, and putting it in my load tester, it does. So no complaints. They're not being bad. They're not lying anyway. So we got battery, and in the other collection of AliExpress goodies, we've got looking for. We'll need those. And then I'm looking for. Jeez, hold on. I can't find them. There is a. Oh, wait, is it this? It might be this little sub bag. Yes, okay. We're going to need a BMS, battery management board, so that we don't cook our LiPos. Or I should say, over discharge our LiPos and break them. Because unfortunately, on another one of my robotics projects recently, I did a stupid. Well, actually, realistically, I knew I was being stupid going into it, but I didn't think it would bite me. Turns out it bit me. Where I thought, let me call it. I thought I would be smart enough not to over discharge one of my batteries, but the problem was that I have a bunch of identical looking batteries. And I grabbed the discharged one and put it into the robot. And so when I left it there, when I plugged it in and then went and did something else for a bit, yeah, totally over discharged the LiPo and it's destroyed. There goes a $40 battery. But $2 BMS from AliExpress. Hopefully this will protect our battery at least sufficiently. This little thing that I threw out of the waste because it didn't look. We might use these. We might need them, I'm not sure. So these are battery charger modules. Actually, I got these off of Amazon, not AliExpress, but these are also all over AliExpress. They look like they have a USB-C port, but they are not PD. They just dumbly assume that they can pull whatever power they're set at. And this one says 4 amps, so there is a very little specification that this actually respects. So, oh well, I guess. The only thing I can think I can charge this with is a Raspberry Pi 4 power supply, because those will just dump, 5 volt, 5 amps, and not, care. Anyway, all right, so, realistically, the way this actually fairly, I missed one component, sorry. We also need, we need an inertial measurement unit. So we'll grab an NP, we'll grab one of these right angle boards. All right, so we'll grab a MPU 6050 board. This will provide our like rotation estimation, stuff like that. So essentially the plan here anyway is that we're going to take this robot, because this LiDAR is very tall, it has this motor that you have to remember to drive. We're basically going to mount this thing sideways. I'm thinking that what we'll do is mount this thing sideways, so that the motor, so that we can fit stuff under it in the center. Like eventually, like I would like to put a camera in the middle here, so that it can do some kind of vision stuff. But that's not going to be part of our base target here. So we've got the LiDAR on top. I'm thinking that I want to put it this way because I want to be able to get the Raspberry Pi under it. And the Raspberry Pi needs to be forward enough so that this rear bit doesn't interfere with the I/O. So hypothetically, it'd be nice to have the LiDAR over the center of the rotation axis, or the wheelbase, but it's not necessary. Anyway, I'm thinking something like that. We'll have the Raspberry Pi. We'll drop this, as low as possible. We'll design a 3D printed like jig that all of this stuff will bolt to. But today we're going to this is the ultimate goal. But at least for this evening, we're focusing on at least getting it to move, right? Or I would like to get it moving before the end of the stream. So maybe we're going to be streaming till midnight again, Pacific California time. We'll see what we get. But yes, so we're going to Pico 2, this board. We're just going to use the scrap of proto board here. The idea is that it's me. So my thought is that I cut this specifically before because I'm thinking that we might be able to fit it. Let me just tuck these wires away in here. I'm thinking that what we might be able to do is, if we are careful, I measured this, but I'm thinking that I'll basically have this board such that we'll build this little thing. I'm trying to just fill airtime here, but we'll build this little thing of essentially that bolts in it'll be a 3D printed frame. There'll basically just be on one side there'll be maybe something in the center that just holds it. We'll drill 2 little bolt holes in here in the top, and then we'll print ourselves a little 3D printed bracket that just holds it on the top here, so there's no flex. And then we'll print another bracket that holds it along the back side. We'll just use these little cutouts. We'll use them as basically screw inserts. So our chassis control hardware will sit back here. And so we'll put the Pico 2. We'll put the voltage regulator. We're going to need to build a little driver circuit for the motor on the LiDAR, because one of the things about the Nito LiDAR is that you actually have to manually control the speed of the drive motor for the spinning. So let's see. That is apparently my catchphrase. Okay. Where to from here? Right. All right. So the other final thing to think about is how to actually power the Raspberry Pi. Okay. Where am I going? I'm thinking of something. The mysterious, horrible cable that shouldn't exist, but yet does because I will it to exist. Anyway, sorry. So how do we actually get power into the Raspberry Pi? Well, there's a little feature of the Raspberry Pi that maybe you don't know about. Okay, now I'm getting concurrent viewers. Okay. Hello everybody new. So we are, I guess we're an hour into this thing already. So for anybody who just joined, we're building the goal here is to build a robot for Robot Operating System 2. It is going to navigate around using SLAM, or simultaneous location and mapping. So the robot doesn't know where it is, and it doesn't know what the environment it's in looks like. So it both has to map and then decide where it is inside that map. the principal sensor for doing SLAM is typically the LiDAR, and this is an old XV11 LiDAR from Anito vacuum cleaner, which is a robotic vacuum cleaner that came out in either the late aughts or the early 2010s. And the XV11 was the first consumer robot on the market that used LiDAR. And now everybody probably thinks about almost all the robotic vacuum cleaners have LiDAR, but back then it was a very brand new thing. But anyway, continuing. So how are we powering this Raspberry Pi? Well, if we've got this board on the bottom here, and we've got this voltage regulator, what is the purpose of the bot? Don't worry about being late. There's no such thing as late. This is going to be a long journey. Purpose of the bot. So it is we're going to call it a research platform, in air quotes. Well, basically what we're trying to, we're just trying to build a starting point for doing, for learning about a framework called Robot Operating System 2. And what we want to do is, we're specifically interested in SLAM, or simultaneous location and mapping. And that's a technique for if the robot both doesn't know where it is and doesn't know what the environment it's in looks like, how do you end up with both of those? And so you are simultaneously localizing yourself and then mapping the environment around you. So the rocket knows where it is because it knows where it is. That's almost like, that video is not correct, but it's almost correct, which makes it really funny. It's not quite accurate, but it's pretty close. For a joke, it's actually closer than farther. Sorry, anywho. Purpose of the robot, really, it's just we want to start playing with Robot Operating System, and it's kind of one of those platforms that, it's kind of, it's got a really high learning curve in order to get into, so just having something, or showing that you can build something from scratch and then use it is cool, because there are a couple of simple reference robots for ROS, but they're all kind of expensive. Like $1,000 for the kit. So we're just trying to build something out of realistically stuff I've got in my bin. So we're going with a Raspberry Pi. We're going with this 10-year-old LiDAR that was a spare part back when I got it. We're going with a robot chassis that I got nearly 18 years ago. Differential drive robot chassis, they're a dime a dozen, but this used to seem cool. Now you can buy this for like $20 off of AliExpress. At least this is made out of aluminum. So purpose is mostly to give ourselves a starting point. Old bin, yeah. So let's see here. Okay, where are we going from here? Right, okay. So, how are we powering the Raspberry Pi, right? I'm curious what happens to the mapping if the environment changes, like if you move the table or something. That is the beauty of SLAM, is it will adjust. SLAM has absolutely no requirement for the environment to stay static. Now, it can help SLAM to be able to give it a static map, so that it has a base reference point, but it is absolutely not a requirement. The algorithm will adjust to the environment changing. So the whole idea of figuring out where you are in the environment is you basically, if you don't have a map and you don't have if you're at the basically t equals 0, with no map, you basically just assume you're at 0, 0. You're at the origin, and you start building the environment around you, but then every move based on that is always a probabilistic model. So you're fusing, because ideally the robot knows its own geometry. So when the robot tries to move, theoretically it can measure its movement. So there's a thing called encoders on these wheels, which basically it's sensors that measure how much they're turning. So the robot kind of has a rough idea of how much it does move. And then the LiDAR will take in whatever data it can see, distances to whatever it can see. And then basically you have an inertial measurement unit measuring, things like rotation and acceleration. And the idea is you're fusing all this information together to try to decide, okay, what did I do? What am I planning on doing? What did I actually end up doing? And what should my new environment look like if I do achieve what I wanted, but you'll never quite move the way you think you did? I mean, you can get very close, but you'll rarely ever exactly move. There will always be some level of uncertainty. But anyway, you're taking all these sources of data and trying to essentially figure out where it all agrees. And so if something changes in your environment, if you drove forward, once 10 centimeters, and your inertial sensor said you moved, at a certain speed for a certain amount of time, and then your encoders say you moved a certain distance, and then your LiDAR, all of the points in it shift kind of the way you're expecting them to, but then some of them didn't, you'll know that the points that are much further away from what they should seem to be are probably something that has changed in your environment. And so the algorithm is fully dynamic. It does adjust to changes in environment. So if it's running around the room and I move a chair, or it'll see my legs. I walk. And it won't. It can tell that it'll take a scan and there was an obstacle there, and then it takes another scan, and all of a sudden that obstacle is no longer where it previously was, but there are new obstacles. In the next scan in a different spot. It knows that those are changing against the map, and it will account for that. And hopefully this is all software we can bring into the robot, because the whole point of using ROS in the first place is to reuse existing robotics algorithms that are written for ROS. Ideally, all we're going to have to do here is build our robot and then write the software that integrates our robot in as a its standard base in ROS. Basically, it expects that there's this kind of sensor. We'll write software to make sure that our sensor is available in that genericized way. For our encoders, our IMU, our LiDAR. And ideally, if we do that, we can just use the existing SLAM software for ROS. And if I switch back to my desktop here, that's a stack called Nav2 in ROS. And it's been worked on by a lot of different companies. I mean, Dextry, NVIDIA, Polymath. What programming language is ROS? It is almost exclusively C++ and Python. The only two languages that are, quote, first-class citizens in ROS are C++ and Python. There's a very comprehensive C++. ROS is written in C++. But in terms of nodes, which are programs that live inside ROS that communicate data in ROS, so there is a Python interface and a C++ interface, and for performance sake, a lot of people will write C++, but for simple stuff, Python's not that much of a problem. It's certainly easier to prototype in Python. If you find out that something you write is a bottleneck, you rewrite it in C++. But it does have, and there are unofficial bindings, for plenty of other languages. But we're going to be sticking with C++ and Python, because the idea of this stream is going to be, or of just this series of streams. We're not finishing this tonight. I'm sorry, but we can't. It's too much work. But hopefully we're probably not even going to get to ROS tonight. We're going to try to build the hardware and make the robot move. That's what we're doing. That's tonight's goal, right? Let's see. So now let's see. Right. So again, how are we powering this Raspberry Pi? Because that's the comment that I was on. We're gonna absolutely fry the battery in my phone doing this. So right, we have this horrible cable that should not exist. It is evil. But it is on one end a USB-C port. It is on the other end a micro USB. And so what we can do is we can take our Pi Pico and we can plug micro USB, into it, nice and connected there. And then we can take a Raspberry Pi. And what we'll do is there is a USB-C port on Raspberry Pis. That's how we get power for both the Pi 4 and the Pi 5. But what we can do here, that is the cursed part anyway, is so a lot of people just think of this USB-C port on the Pi 5 as a power input, and it is, but it also implements a USB 2 connection. We can actually go into the config.txt in your Raspberry Pi and enable a USB 2 connection on this port. And it does a little bit of funky things. At least with the Pi 5, it's compliant. We're not going to be compliant, but the Pi 5 does have full PD compliance, so it can negotiate, I am a data provider power receiver, and follow the standard USB-C, device negotiation role what is it called? Role determination protocol. Role discovery protocol. I'm sorry, I don't quite recall off the top of my head. But Pi 4s just assume that they can get whatever amount of power they want over this port, and if there's USB, there's USB. So what we're going to do, we're going to enable the config.txt on this Pi. We're going to turn on this USB-C port, and we are also going to override in the Pi 5's firmware that to just suck whatever power it can over this port and not respect USB power delivery, which all sounds very cursed, but I swear it works. I have tested this. With this cable, in fact. Again, sorry. So the idea is that what we're going to do, the Pi Pico has the power pin on USB that supplies power is called VBus, and on the here, if I can zoom in, the Pi Pico, if you can tell, on here, and just to be transparent, this is an A2 stepping Pi Pico. Or Pi Pico. This is the RP2350, so Pico 2. This is the A2 stepping, so this is... It kind of, sort of has 5-volt compliance, but also not. But we're going to pretend that it does, because it should be fine. But if you buy one of these today, you'll get the right one. Because I bought these 6 months ago, they're not necessarily the good ones. But anyway, the VBus stuff. So VBus is the pin on the USB port that carries the power. 5 volts for standard USB, or if you have PD, it's whatever, a negotiated line voltage you have. In this case, everything's 5 volts. On a Pi Pico, this top pin, this top pin, which is pin 40, is connected directly to the VBus pin of the USB. The second pin, which I believe is called VSys on the well, that's a Pi Pico terminology, but I believe it's, I can turn it over and read it. Okay, so the second pin is VSys. And the only difference between these two pins is that this is directly connected to the USB port, and the next one is there's a diode from VBus to VSys on here, and then VSys supplies the voltage regulation circuitry on the Pi Pico. So if we were being fully good, which we're not, but if we were being fully good, what we'd do is anytime we wanted to give an external power supply to the Pi Pico, ideally you should run it through VSys. And the reason that you should do that is if I were to plug a USB cable into the Pi Pico, and it's trying to supply 5 volts from my computer, and if I were to connect a battery to VSys, let's say I connect a 3.7 volt battery or something, because the current, or well, actually, let's just say an external power supply, some kind of external power supply, battery, it's something or another. If I connect if I connect the power source to VSys, if it's higher, I'm being overcomplicated. Either way, the diode prevents current from flowing backwards. So if I have an external power supply for my Raspberry Pi and I connect it to VSys, and then I plug my computer in on the USB port, there is no way for power to leak back out of the Pi Pico and then into my computer. Regardless of whatever voltage I have set on the VSys pin, current will not, there's a diode there, the current will not flow backwards. We're going to be bad, and what we're going to do is we're actually going to connect our power supply to the VBus pin. And that seems like a horrible idea, and it typically is. But the reason that we're going to get away with it is because since we're backfeeding current into this cable, and it's connected to a Raspberry Pi, so that will power the Raspberry Pi, because it wants power in on this connector anyway. So we're kind of just jankily supplying power to this single cable power and data, to our robot chassis over the Pi's power input, which just simplifies. Did my phone freak out? Or my phone's starting to overheat. I hate Pixel. All right, we're gonna have to switch back to a different feed so my phone can cool down. Let's see. So otherwise, you have to watch slow FPS. Anywho, right. So that'll be how we power our Pi. And we'll do that. So, next what we're going to do, so now that we kind of got our rough idea, the one, I guess there's just one little final component to explain, and that is these motors. So you may have noticed, if you've built any of these little robots before, that I have not talked about a motor controller, and that is because these are not the original motors for this chassis. These are right. I overheated my phone, so let me just minimize that here for a second. Sorry, let me put my phone in. And toasty. I really appreciate how most modern phones, this one, Pixel 5 is kind of old now, but I do appreciate how most modern phones are able to, what do you call it? Jesus. The video encoders are efficient enough that the phone doesn't heat up too much. But anyway, I've made a mess on my desk. Okay, so the cool thing about the let me just swing this thing out of my face. I'll try to use my webcam for this. So this motor, these, you know what, let me just, okay. See, there's a lot of wires sticking out of them, more than just two that you'd expect. So if we go, these are a brushless gear motor, 37 millimeter. Yeah, so these are these kind of motors. I didn't buy them from here. I bought them from Amazon, I think. But these are essentially, if you've ever built little robots with those 37 millimeter gear motors, which have been popular for ages now, this is actually a brushless version, which is kind of cool. They have a lot less noise on the power rails. But the cool thing is they actually integrate the motor controller. So all these motors, all you have to do is you give them 12 volt. You give them a 12 volt power rail, or around 12 volts. It doesn't have to be exactly 12 volts. It doesn't have to be regulated, but you give them a generally 12 volt input. And what you can do then is you just give it a PWM input, a direction input, and it gives you an encoder pulse train feedback output of it. And no brushless motor controllers. So realistically, all our board has to do, our little board here that we're going to try to build, all it has to do is turn the battery voltage from 12 volts to 5, or we're going to use a 3-cell LiPo, so 12 volts to 5 volts to drive all the electronics. We'll feed the 5 volts into the Pi Pico. Just feed the 5 volts into the Pi Pico. Pi Pico will supply the Raspberry Pi. We just need 2 connectors, one for each motor, and then we'll need to connect 2 connectors for the LiDAR, one for the data, one for the motor driver, and then we need so motor driver, one connector for each motor, 2 for the LiDAR. We then need to add a connector to plug our IMU into, and that's honestly it. So it's actually a really simple little board, thankfully. So we're going to start by, I haven't soldered headers to any of these Pi Picos. So I think what we'll do is, I'm going to move this monitor arm here over to the desk, and I will solder the connectors onto this Pi Pico. And the other thing that we want to do is we kind of want to evaluate how well this little voltage regulator works, because the listing claimed 5 amps. Looking at it, I can possibly believe it, but not. I've been burned by literally and figuratively burned by these little boards before, because they always claim something a lot more than they're actually capable of, right? But anyway, so let me, so you don't see me, I'm going to turn off the webcam, and I'm going to move this monitor arm over to my workbench here. Technical difficulties. I'm just staring at a motor listing. Okay. How much is the usual discrepancy of the overpromise? It can actually be quite substantial. So I have a couple. Actually, here, let me Hold on, let me put this down. I'll show you. So let me pull out some. Let me pull out some examples that are on my shit list. Anyway, and if I'm feeling extra spicy, maybe I even show you the listings so you know what to look out for. So here, let me grab some of these. All right, grab a couple of different voltage regulators that I've bought over the years. None of them are capable of what they claim. And I will pull out one that is absolutely capable of what it claims. So, let me switch on my webcam here again. Now the camera arm's over there. Okay, so this is probably the first little board that I bought. They're very prevalent on Amazon. Let me just bring up an Amazon list. You know, I'm gonna just so you don't see my family Amazon. Let me private window Amazon. Let's just say 12. Let's just say step down switching regulator, switch converter. It's almost certain to come up. Oh yeah, here we go. Second hit. These are ass. These suck. These are bad. So they claim. What do they claim? They claim. Okay, this one's actually fair that it only claims a 2 amp current. That's capable of supplying 2 amps of current. That's a fair claim. That's about what this is capable of. And with 3 amps, you need out of heatsink, and that okay, fine. That's a fair claim. But the board is, it is substantially, it is quite large. If you put it next to a Pi Pico, for instance, it's almost the size of the Pi Pico, but yet it can only supply 2 amps. And if you think about something like a phone charger, those can supply 45 watts, and they're also switching AC, converting AC, and yet they work fine. And they don't get hot, but yet this thing, you try to pull, if you try to pull 2 amps out of this, it gets warm. If you try to pull 3 amps, it gets really hot, and it hurts if you touch it. Which means, because it's getting so hot, switching, providing such a small amount of power, 2 amps, 3 amps, so 10, 15 watts, like it's probably only like 60-something% efficient. Like, it's throwing a lot of it's better than using a linear regulator, but it is still throwing a lot of that energy off as heat. So not good. And one of the ways that you can on these that you can kind of tell visually is what kind of capacitors they use. This is, okay, let me start off. Anybody watching this in the future, gross generalization. But if you look at a switching converter and you see big fat capacitors, these silver cans on each end, if you see electrolytic capacitors and you don't see any ceramic capacitors, so and when I say ceramic, I'm talking about like the kind that you'd kind of think you'd see on a PCB. They're called MLCCs. Yeah, so if you don't see any capacitors that look like this, and you see big electrolytics, you already kind of should have an inkling that the regulator's going to suck. Because high efficiency switching regulators need what's called a low ESR, or equivalent series resistance capacitor, and the MLCC capacitors, the worst of them are several times better or several times lower ESR than the best of the electrolytics. And so that basically you can kind of think of the ESR as going to be the parasitic. It will show up as a parasitic effect on your switching regulator when you're building them. So if you don't see any ceramics on one of these switching boards, just don't. If you can avoid it, don't buy it. So these LM2596 based, or an equivalent would be the XL6008. They suck. Avoid them if you can. And then similarly, I should say, so another one that's kind of on my shit list. Actually, maybe I'll show you another shitty one first. So there's this one, so I should say, yeah. So this one says 2 amps, says 3 under load. That's a fair claim. They're just not good. This one, on the other hand, claims that it can do 5 amps. And it is true that it won't catch on fire if you try to pull 5 amps through it, but I did set it on my bench for a while. Let me pull up. I believe that I bought this on AliExpress, which should give you an idea of anything. let's see what horrible things AliExpress tries to put on. Oh, geez. I really, why did it go to Ali? Why is it in Spanish? All right. Okay. 5 volt, 5 amp, AliExpress switching regulator. Okay, maybe. Yeah, here we go. Which one is this? This one is. There's gonna be a lot on here. I'm trying to think. I got this one is so yeah. Here's another one of those XL series boards or XL4015. It's the same problem. I'm trying to find this exact one that I bought. I'm just throw USB on here. Yeah, here we go. This one. It only costs Why is this in Spanish? I mean, I'm in California. Maybe. Oh, okay. I might just see that I'm in California and figure Spanish is probably a better choice, and it's probably not that wrong. But anyway, this board, not good. Claims, yeah. So claims 5 volts, 5 amps, so 25 watts. At 2 amps, so 10 watts, it starts to get pretty warm. And if you do 4 amps, it starts to get way too freaking hot. And at 5 amps, the voltage output starts to droop, and like you can, and it won't catch on fire, but it really shouldn't operate at that point. I have boards that I bought, or voltage regulation boards that I bought a decade or more ago. They can run the same amount of current through them and not even be perceptibly warmer than the air. But again, this costs $1. Whereas something like Pololu, which is a good brand, but I bought step down converters. I don't think they sell the one that I bought years ago anymore, but here's also kind of what I was talking about. Like, you can see all of these ceramic capacitors on these regulator boards. This one does, I mean, this one's just 1 amp, but where is the higher output? Do they not sell the high voltage or the high current ones anymore? They might not. It just depends on what their market is. I think it was... Well, actually, if we go to my GitHub... GitHub, Kubernetes, Logic, PD. There we go. Yeah, so this board that's on this old Pololu, or this old Pololu switching regulator, I mean, okay, just seeing a ceramic, just seeing an electrolytic cap's not like necessarily a bad thing, but you also want to see bulk decoupling caps that are ceramic. Like the whole point of using these caps is if you put 2 resistors in parallel, the overall resistance is less. So the more capacitors you put in, the whole thing was that if you stage things such that, okay, you've got the switching regulator and then nearby you have really low ESR caps or ceramic caps to handle the switching parts, and then you can put larger, slower capacitors a little further away from it. But if the bulk of your decoupling capacitance, or not decoupling capacitance, if the bulk of your energy storage capacitance on a switching regulator is an electrolytic cap, they're going to get hot, because it's just they have a higher resistance. But so this board I bought the switching regulator back in oh yeah, here's the part number. But I bought this back, I think it was early 2012. Yeah, so early 2012. It was rated at it's a 12. It's, I believe, up to 30. I think it's up to 30 volts. Oh, it's up to 24, but they discontinued. But it's up to 24 volts in, 5 volt out. At 5 amps, which is my typical draw on this, it's barely perceptibly even warm. Whereas these 2 boards I got off AliExpress, these things are borderline burning. Like the burning meat. It will burn your flesh if you touch it. They may not be so hot that they'll destroy themselves, but they're going to run real hot. I'm going on a big tangent, but. Something that so if I've been talking about things that do suck, let me talk about things that don't suck. So on Amazon, there is this thing called the Thomson 24 volt 5 volt. or 5 volt 50 watt. So this little guy, Home Life Thompson. I mean, again, we've gone from $1, to $10. So if we're gonna pay 10 times as much, then you'll get one of these. And these are awesome. And these do everything they claim. I have pulled, 5 volts, 10 amps through this 50 watt rated board, and it gets a tiny little bit warm, at 10 amps. But other than that, works great. Does what it's supposed to. Does what it claims. A plus. But again, these are large. I mean, this one compared to one of these shitty boards from AliExpress, it is quite large, or compared to a Pi Pico, it is a large unit. So you can definitely get a smaller board. I mean, 50 watts is overkill, but for this. But heck, you only officially need to supply a Pi 5 with 25 watts, and the only reason you need 25 watts is because it wants some overhead for the USB. It wants some headroom for the USB ports. The actual board itself pulls slightly less than 15 watts at full load. Again, yeah. So XL or LM 2590 something or another boards, avoid. Whatever the hell this was, avoid. These are also kind of crap. Again, these are Amazon 5 volt adjustable switching 3 amps. I think these were officially called. Yeah. Here was the one that was big on my shit list. Okay, yeah. So yeah, it says so again. It claims 10 watts, which it don't. So yeah, it says can pull 2 amps continuous, max 3 amps, just like the other one. And to be fair, off the bat, it's full of ceramic caps, no electrolytics in sight. You'd think it'd probably be fine, and it does get very hot. It does, again, gets hot. Probably some pretty cheap components. Not nearly as horribly hot as the other one, though. But I would say it could do 2 amps, but it does get very hot. It's very inefficient. They claim a conversion efficiency of 97% with a typical value greater than 90%. Utter bullshit. That is no way. So careful with voltage regulators. If I spend the $5, spend the $10, get a good one. This voltage regulation is not something to cheap out on. Let's just put it that way. So with that rant over, we're going to evaluate these, and I believe these were effectively $2 a unit. So still quite possible that it sucks, but I have a little bit of hope for them, because they claim, or I think it's called the Mini 560 Pro. I have okay, so yeah, so again, I did pay cheap on this. We'll see if that worked out for me or not. But we're happy to see that they have ceramic capacitors, again, lots of them on the output. I think that's the output rail. The output rail. So they got ceramics on the output rail, they got ceramics on the input rail. I have the one on the left. So yeah, the circuitry is done fairly tightly. The switching circuit is very close to the inductor. The inductor is probably substantially oversized on this board. These capacitors are far away from the switching circuit, and the name of the game in switching regulators is you absolutely want to keep the capacitors as freaking close to possible. Like, you want to make the circuit as small as possible. Like, I'm surprised that the feedback network over here is closer than the actual energy storage / decoupling caps. It's not necessarily the best sign, but again, cheap. This is cheap stuff. Like, I can't complain too much. If I paid $2 for it, it sucks that I should have spent more than $2. But anyway, what are we starting with today? I'm ranting. So I'm gonna go set up the arm, and we'll at least we're gonna start with we're gonna solder the headers onto the Raspberry Pi Pico. And we're going to solder some connectors onto this voltage regulator to kind of just do a little bit of evaluation on it, see how bad it is, how good or bad it might be. And so let me continue doing that. I'll pull back up the whiteboard, and I'll turn off my webcam so I can go set up the other thing. It's not wanting to stick to the edge of the table. Hold on, technical difficulties. Okay, I got the thing mounted. Okay. Okay, just a second. Let me mount my phone up here. Okay, let's see here. Let me on the webcam, desk cam. Let me turn on. Hold on, I'm trying to figure out how to get the audio to start up on the Droid Cam. I had it before, but I'm having difficulty with this. Let me start it with audio. App. Settings. Audio. Coming in upside down. Okay. Anywho, why is this being such a pain? Oh, there we go. Okay. At least that's on that. Let me You know what? I don't understand why the audio is being such a pain. Oh, you know what? It's probably not the phone. It's probably my configuration of my. Oh yeah, that's why. Deactivate, enable audio, activate. Okay. Sorry, that was an OBS setting, not a that setting. Okay, cool. We good now. Perfect. Sorry. Let me grab stuff. So we're going to test. All right, cool. We're gonna do some of these voltage regulation stuff. We're going to test. How are we gonna test this? We're gonna test with. And get some wire, connect it to that. We'll solder some output lugs onto it. Let me grab my load tester. Grab the load tester. Grab some wire. Red and the black wire. Plug in the soldering iron. Soldering station anyway. Okay, I'm gonna actually need to go get my power multi-strip. Okie doke, multi-strip, wired. Yeah, well, don't break things. Here we go. Okay, right. Perfect. Do that, power this up. Hopefully that cable will be long enough. Anyway, power up the soldering station. And then, there we go. Away. All right, so I need the pins to solder in here. Those. Grab the ones for the debugger. Looking for pin headers, but all right. That. This. Okay. Perfect. All right. Get to work. Okay. So bring soldering chemicals over here. Soldering iron is heated up. Got my wire cutters. So yeah. First things first. We're gonna test this voltage regulator. So we're gonna. Do a little clippy here, solder on some sacrificial wire here, cut ourselves some test wires, cut ourselves some black wire. Hopefully people can hear me. I think I see it out of the corner of my eye. Okay, so. I'll get that one. So yeah, we're just making ourselves some little connectors to essentially solder onto this board here. So we'll just
way for give ourselves some little rotation here. Spin these up a little bit. Put this over here. Do a little isolation flex. Over here. Get some flux, which is just a nectar of the gods from a soldering perspective. All right. Oh. Iron. Dupe. Dupe. I reflex that one up. Cool. Perfect. Black wires. Oops. Oop. Oh well. Yeah. Two. Two. All right, cool. So, solder on the. Oh well, we'll just do one at a time. Makes my life easier. Okay. Okay. All right, hold on. You know, a lot more solder than that. There we go. Good. Okie doke. This is the output side anyway. All right, so solder the other one. Okay, let me just use tools available to me. Cool. I got those ones done. the other one's kind of fast. So I'm gonna do this. Yeah, so we're just tinning the wires here, so it's easier to solder them to things. So we're just using some flux, and that'll make solder wick on these wires so much easier. All right. Black ones. All right. Ow. Perfect. Okey-doke. So spin this around the other way now. Put the iron down. And to do this positive rail. All right. Yeah, I want to do this. Yep, they messed that up. Okay. Really, really ought to just try to line this up perfectly so I don't have to hold it. There we go. Perfect. Should have just done that the first time. All right, I'm gonna do this last one. Okay, cool. All right, now we can actually test this. Okay. Turn the iron off, free this. All right, ew. Pull on that too much. Ow. All right. Yeah, let me go check the comments. Hear you, at least for now. Okay. You gonna flip camera on it? Yeah, I hope I was able to do that. Hey, kitten. How you doing? Kitten. Yeah, okay. Now what? I need... Got that. I got the load tester. Cool. Okay. So now what we're going to do is... Oh, there's my screwdriver. Okay. All right, so I'm going to change this adjustable power supply to 12 volts to simulate the battery. And cool, 12 volts. I'm going to take this. We're going to take these out. This is the input side, so we're going to do this, plus to plus. I need to unscrew these more. right, so that gives us plus on, so the red is the plus, so we did red is plus, black is minus, red is plus, black is minus, all right. So now, I'm just going to button this back up, pull out the load tester, which is a device which you can program as a variable current sink, which means that it will adjust how much current it's pulling to, it's either, yeah, you tell it how much current to pull and it will pull it, just so you can test kinds of electronics. Okay, let me do that. Okay, how does this work again? Yeah, I see, okay, cool. There we go. So, we gotta put in little cross wires. The high current lugs are these outer ones, and the inner ones are just sense lugs. So I'm gonna screw these ones in to the inside first, just so we can sample. The high current. All right, do this one. Yeah. Okay. Okay. Oh, damn it. Right. I'll do that one tight enough. Okay. Oh, we've got our load tester hooked up. Take a load tester power supply, or load tester's power supply. Plug in both of these power supplies. 12 volts. Try not to watch yourself. All right. Alrighty. How much? Oop. Too bad. That's horrible. Whatever. Okay. And then let's let this power up. And hopefully nothing explodes on me. Cool, we got 5.11 volts out. Okay, it's still here. Yeah, alright. 5.11 volts out. We've mostly cooled down. We've cooled down from soldering, so we're not getting any unexpected heat. So let's program 1 amp of draw, and cool. We can pull 5 watts and make it only just a small voltage drop. Let me start upping the current here to 2 amps. Cool, we only got 5.06 volts on drop. Let's see. Let's go broke. Let's try 2.5 amps. So we're going to try half the rating. See, we're pulling, well, it's probably hard to see through the camera. So there's this, you know, if I turn on the light here, you might be able to see better. Just in terms of reading this. Nope, that didn't help. Hold on. I'm gonna just hold this in my hand here. Maybe it'll. Yeah, so we've got 2.5 amp draw, 5 volts out, so 12.6 watts. If I hold my finger on the regulator, it's That's tiny tad bit more. It's not room temperature, but it's not that much different. This is already substantially less heat than those other two regulators I showed you. So we'll go broke here. Let's dial this up to 3.5 amps. So yeah, we're still at 5.03 volts out, so we're regulating very well. Oh, whoa. I flipped the camera. Hold on. Back. 0. There we go. And hopefully flip. Wait, let me. Oh, I gotta flip the camera for you guys. Where did that setting go? Hold on. There we go. Oh God, has this been upside down for you the entire time? I think the answer to that is yes. Oh man, I'm so sorry. Okay, so we're at. Oh God, I'm trying to figure this out. Now it's diverted to my view. Okay, so we've got 3.5 amps, and it's warm. It's not horrifically warm. It's not comfortable, but the fact of the matter is, the robot. This is what, yeah, this isn't the most fantastic thing. And realistically, it's the inductor heating up. I think, no, it's not. Wait, what's heating up? What can I feel heating up? It's the switching element. Okay. So, I mean, it's not perfect. There are better options. But again, this is performing better. And again, it only cost $1. What happens if we go? Once we go the full 5 amps. Watch it explode on me or something. Well, to give it mad props, the line regulation has been good. We're playing a substantial number of amps. Ow. All right. Now it hurts to touch. Ow, ow, ow. Okay. Well, it's not the worst I've seen, but it's also not great. 3 amps. Oh, what is happening? Okay. Technical difficulties. Okay. Yes. Anywho, okay. Let me just undo whatever I was just doing here. Okay. So, that could have gone worse, maybe better, who knows. Okay. Unheard. Okay, cool. Anyway, regulator's not the best I've seen. It's not the worst I've seen. That's fine. It'll be sufficient for our uses here. So now we're going to. So what are we doing now? We're going to do. Well, let's actually start. Yeah, we'll put the wires on the Pi, and then we'll do some other stuff. Okay. Unplug this before I start unscrewing things. Together. We'll test it away. tester away real quick. Okay. That there. Okay. Okay. Flow tester, put away. Cool. Okie doke. Okay. So wires. Okay. I mean, we got. Sorry. We got this. Let me pull that. There we go. Let me grab another one of those voltage regulators. Okay, so another one. All right, so planning. Let's do a thing. All right, we need to solder the headers onto the Pi Pico. We're going to do that by turning the iron back on. Say Pico 2W. That heat back up here for a minute. So much writing. Okay, so that's going to go that. Got some headers to mount things to for the Pi. So these are the 20 pin stack throughs, so I can stack on this. I never actually figured out what I wanted to do on that front. Just a second. Okay. Alright, we're getting a little bit of planning. Alright, so let me just make sure I'm sharing. Okay, so we've got, if the idea was and put the Pi with the ports pointing backwards, we've got, the power connector. It's coming down through here. Then we want to be able to route the connector. Actually, I guess it really doesn't matter what side it goes onto now, but if we wanted it to be on the same side, we would need the connector to come in this way, which means if the wires are facing, if the screw holes are facing towards the bottom, we want the Pi up here pointing to the left side essentially. So holes down, Pi left. So we'll just do it like that. Okay, cool. Okay, iron's heated up, so. Oh, I left the Pi. Okay. Okay. Right. So, Pico. Start soldering this on. Oops. All right. Alright, so let's just make sure that it's not bent over. We melt this. There we go. Now it's all nice and vertical. Let's get the other side as well. Oop, that was, oh, dang it. Right. There we go. A bit more correct the first time. There we go. Perfect. All right. Now we start the soldering. Okay. Alright, soldering all 40 of these pins. Not the quickest process in the world, but it'll take that long. Soldering is actually a pretty cathartic activity. Either that or it's the flux fumes talking. Cool beans. So we got those. Okay, these 18 left. Go back and forth. Be a little more fun. Do do do. All right, it's mostly visual activity at the moment. Try not to lose my foot. There we go. There we go. All right, we got one pi pico. Okay, well, with the I/O header's installed anyway. Let's put the debugging header onto it. For that, I need a little bit of scrap in here or something. Not sure. Pretty sure I keep scrap. There we go. No, that's an angled one. Oh, come on. I have to have some pieces of scrap. There. No, that's 2 pins. Wow, okay. I'm gonna cut 3 pins off of this. There we go. It's fine. That's not pretty, but what we can do is a little funny here. There we go. I think that's mostly the correct orientation. Not quite, but close enough. Okie doke. I'm putting the debugging header on. Okie doke. Got that. Alright, so we have a Pico 2W with the debugging header on now. That's nice. Now, so don't forget, we're just going to tack down these Raspberry Pi headers, or the headers to install the Pico. Alrighty, that's what that would look like, and then this would go next to it. Okay. Or let it under there. Nah, not quite. Almost, not quite. Anyway, okay. I'm just gonna do that. What the heck? Kittens are playing with stuff. They're not really that nefarious, but alright. Oh, there's the corner. Interesting. Okay. Interesting. Okay. Oh. It's popped up a bit. Alright, I'm gonna fix that. There we go. Alright, that's okay. Well, maybe we'll move that depending. Okay, so now what? Our little board there. Okay. So, actually, to be perfectly honest, I think we're gonna have to put screws in the middle to hold things down. We might want to drop it another rung. We definitely have the room for it if we solder this over here. Yeah, okay. I'll move it down one more tier. Just got solder right now. Almost out of this one. Solder these in the wrong spot. Okay. Go quite as expected. Well, okay. That went so much worse than expected. Okay. Well. managed to block up the nearest 3 holes. That's cool. That's cool. Cool. Alright, I'll just cut off the least bit of the braid here. And try this. There we go. Let me see if that was good enough to pull it out. Nope. Oh, oh, well then. That's what I get for using cheap connectors, I guess. Okay, that's fun. Ah, sorry, bang the camera again. Okay, well on that note, okay, put that back. Come on. All right. Well, we'll table that for later. Okay. I'm a little. Okay. Hold up. We're just gonna do this old-fashioned way. No. I did it again. Okay. Hold up. A little bit. Out. Oh, hold on that again. Damn it. Okay. Ow. Okay. Okay, this is utter stupidity. Okay, why? Why is this? Oh, that would be my luck, wouldn't it? Okay, we're gonna table that, for, at least for the moment, and let me do a thing here. We're probably almost the power on my phone, too. 33% fine. Okay. All right. I keep saying I want to table it, but I don't want to table it. I'm gonna figure this out. I want to know why, or not know why. I just want to fix this. Okay. This one. Okay, pulled that one. Pulled that one. All right. Okay, cool. Okay. That was irritating. And almost the holes are clear, but not quite. Okay. Let's put these back together. Okay, when I dropped, there it is. Okay. I do that a little differently. Put that one there. Okay, cool. Okay, sorry, I'm not talking much. Just put the focus up. I'm supposed to be entertaining you with the lovely sound of my voice, but I'm trying to focus. Okay. Okay, come on. There we go. Fine. There we go. Oh, almost there. Perfect. Okay. Okay, cool. That's all I wanted to do. So I wanted to get the pi picos, or like the socket for the pi pico, mostly situated. No, without pulling those out. Come on. Sure. Okay. So those are that's mostly situated, and then we will take the voltage regulator, and this is the side. We're basically gonna solder the output. We're gonna solder the buck converter here over here essentially, and run a cable up to the top of it. Oh, dang it. All right. Well, actually, it doesn't really matter at this point. But actually, instead, what we'll do the outside. Side negative, negative, positive. Or we do it over here. Like, I don't have any strong preferences. Originally, I was thinking I was going to do it like this, but with the way that we wanted to mount things, it wasn't the best thought. I mean, I could have pulled the pi pico down. Anyway. Yeah, so we'll probably mount the regulator kind of like this. Actually, that's a plus sign, which is the opposite again. Plus. We'll probably mount it. Output side. We'll probably mount something like this over here, and we'll probably mount it something like this. Put a terminal block over here to supply power Okay. Yeah, we'll probably we'll should move it down one more here. Yeah. Put a terminal block over here to supply current, and we'll probably put the two battery connectors like on the flip side over here. I mean the two motor connectors over here. The battery will screw in here. But yeah, okay. Oh, worse than expected. Sorry. Yeah, I'm over here, so I don't see chat. Okay, worse than expected, as in the little tabs had popped out of this connector, and I was having a lot of trouble. Had a tiny bit of trouble desoldering it, but other than that, we're fine. And then the other idea will be we'll solder the MPU up, or the IMU up like this, and because this is mounted like this, we're going to need this to kind of point up. And whatever cross brace thing that we design to hold the PCB will also hold the IMU. We'll make sure that it can screw into the IMU as well, just to give it some stability. And yeah, do that. Okay. Okay. So, now what? Okay. All right. The kitten wishes to snuggle. I might have to take a kitten break. The kitten wishes to snuggle. Hi, kitten. How are you doing? Oh, do you not wish to snuggle? Do you want down? Oh, you want down. Why'd you jump on me then? Okay, you go over there. I don't want you on the desk with a soldering iron. I don't. Okay. I'm gonna plan this out. Okay. I feel like we should do a breadboard test first, but I don't know how well that's gonna go. These might not be. I can probably squeeze those into a breadboard. That's probably doable. Okay, well, take a slight tangent. And what we shall try to do now, or not try to do now, take a bit of a detour and talk about battery protector. So these lithium batteries, or lipos, anyway, they have what's called a balance connector. Well, so if you see there are two cables coming off of here essentially. You've got this one, which is your standard, the main power connector on them. It's a high current. These are very thick, 12 AWG wires. These can probably handle these are it's probably 50 amp wire. Like they're high high current capability. These ones are it's called the balance connector, and it actually basically all the little wires tap between the cells. So the red and black are still the positive and negative rails of the whole pack, but each of these yellow wires is tapped between the packs. So it lets the charger try to make sure that each cell is charged equally. But the connector on here uses a 20 gauge wire, so you can actually run like 5 amps over. Hey, kitten, what are you doing? What are you doing, kitten? Hey, what are you doing? You trying to attack my wires? Is that what you're doing, you little wire shark? You little wire shark, we got kitten, who wishes to explore everything I'm doing because she's very cute and cuddly and very curious. Yes, she's also kind of tired and is looking for somewhere to sleep. Yeah, okay. Yeah, I know, you're very curious. This is very interesting. I'm sorry. It's dangerous up here. Immediately turns around and tries to crawl up my leg again.
logic I be, where you be. She especially, she's not even 4 months old yet. She's very very cute. She's very curious. The other one is a little less curious, but this one she would like to be, as you said, be everywhere I want to be, which is a marked difference between her and my previous cat. I love them for it. So what we're going to do here is we're going to integrate this to basically protect this battery. And the way that these balance chargers work, or these battery protectors, is they do have a tap for every cell. So we got the battery ground, 4.2 volt tap, basically pack ground, cell 1 center tap, cell 2 center tap, and then cell 3. So I bought some wires here. This is the male and female versions of these connectors. And so what we'll be able to do is plug, this will plug into the balance connector of the battery. And so I need to actually rewire this connector slightly. I don't know how I'm going to do that. It looks pretty in here. I don't know how the release. Oh, I look like I have to stick a little tiny pin down in here. If I do, I might be able to release the connector. Only reason I want to do that is because the wiring doesn't quite line up to the wiring of these from just whoever designed it. These aren't necessarily meant to be the same thing, but they're not the ow 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 ow. Okay, hi kitten. Do you want to get all the way up? Huh? If I turn off the soldering iron, let me turn off the soldering iron so you're fine. Okay. I know, kitten. I know. You're very curious. Yes, very curious. I just don't want you on this desk, okay? You like to eat wires. And you're still young enough that you want to eat wires. Or push things off the table. So I gotta make sure that you don't get up here. And you're very irritated at that. She's like, I have never been irritated at you yet. What is this feeling? Okay, let me try to find a tiny, do it. Trying to think of what I have that's long enough to shove down the, to disconnect this. Where's the kitchen? I don't want to run over your tail. There we go. Anyway. So yeah, because that's not, it's long enough, but it's not strong enough. Okay. I need to find another solution. Basically need one of those phone SIM eject tools. It's too big. It's too big. All right. Small enough. Nope, not small enough. Okay, almost small enough. Not quite though. Okay, think. I got that I can push down there. Maybe my tweezers. Yeah, that might work. Actually, I mean, who knows? Oh, hey, there we go. Got it. Okay, nice.
watch that never work again. Again, we're just trying to get the wires out of this housing so we can try to color code it as close to the battery as possible. Watch me break my tweezers. Fuck. How did I accomplish that before? I got lucky and I pulled one out, but what do these actually look like internally? Yeah, I mean, how does that even, what does this mechanism look like anyway? Since we're gonna need to figure out to release the wires. Okay, that felt like it did something. Oh, there we go, cool. We've already broken the release mechanism or something. That would be really ass. Right. I need the red wire to come out. It's in the wrong. It's the only color code that's in the wrong place. It's the last color code that's in the wrong place. Oh, I really bent it. Oh shit. Bending my precision tweezers. Okay. Come on, please work. Come on. There we go. I think I got it. All right. Now, I felt the release clasp move, but fuck. Fucky. There we go. Cool. Got it. It's upside down. Okay. Nice. Perfect. All right. Oh, we've thoroughly messed up my tweezers. Okay. Perfect. So we would go on like this. You can feel that it clicks, which is great. So we want the dark one in here. Watch me destroy this connector. Oh, there we go. Cool. It relatches. Nice. I did not break it. Perfect. All right. Nice. Not too badly, anyway. Oh, this one. I really peeled this hook up on this one. What does this one look like? Oh wow. Yeah, I did peel this hook up real bad. Okay. Try to push that back into the shape it's supposed to be. Alright. Working on it. Okay. Right. Back to the tweezers. I think you got that in there. I think I got that in there right. Yeah, there we go. Cool. that's secured. Oh, that one doesn't seem to want to latch. Okay, that's not good. Alright. Fuck. Alright, hold on. That's not good. I have this feeling that I just... dang it. Okay. Well, that's unfortunate. I broke this one. Too much, what do you call it? Okay, what we're gonna do is we're gonna try to pull this little hooky thing out a little more. Maybe that'll be enough to catch the hook on the inside. Basically, we're trying to get this in without damaging the locking. I damaged the locking mechanism, so if we put that in there, looks like it might be enough to stay. But anywho, all right. So I nicked this wire. Okay, we'll have to think about that. Anyway, okay, cool. So now I'm not gonna plug this in because I got bare exposed stuff here. But now we can see that under here the main, the red and the black line up, and there's just yellow and white. Oh, I'm holding it out of view. Okay. Yeah. So the yellow and black. The red and black in the batteries connector lines up with the red and black on this external connector, and then the center tap is just the center tap. So we don't have to. They're linear. We don't have to worry about it. So what we'll do is we shall figure out what that looks like to connect it to this balance connector. And it looks like, because the whole 0 volts positive voltage thing, if we connect, we'll use the red kind of as our benchmark here, and we'll cut the other wires down to whatever we need them to be. And so the yellow and the red will split across the here where they're supposed to be soldered to, and then we'll just tap the other ones as necessary. So let's start with that. These look I turned the iron off, but we'll do that. Let me move the spicy pillows over. Well, it's not spicy. We don't want it to become a spicy pillow. There. What would the alternative of soldering? Like a decoy keyboard? Yeah, exactly. Decoy keyboard, exactly. The iron heat up. There we go. Iron is pretty much heated up. Okie dokie. Let's see if these are tinned already or not. They're probably not. But we can try. Oh, these are absolutely very tinned. Okay. So we'll just do what we do. Solder the pads here. solder. Sorry. Everybody's world's shaking now. Okay. Soldered that. All right, that's one cell down. All right. Now we gotta make the rest of them line up. Okay. Which will be, we'll just cut off this here. Some wire to strip. Oh, hey, look at that. We can do that. All right, cool. Perfect. Okay, almost there. Do that one connector. Do. Okay. Flat cutters here. Trim off this. All right, cool. Just tap this up a little bit here. Okay. Nice. Got it. Perfect. All accidentally put this twisted in here. Okay. Okay, there we go. A little twist in it on accident. Okay, that's fine. That's fine. It's fine. Okay. Yeah. Okie doke. Tip it up over here. Okay, cool. Well, in theory, this is good. You know how theory and practice tend to go, right? Okay. No, let's at least just make sure there's no dead shorts between these. Okay. And then... I guess we can probably shrink wrap this thing in the end. Yeah, so got that on there. Okay. All right, so let's just make sure there's no dead shorts between these cells so we don't blow it up. Okay, we're looking for continuity. So if we touch these, obviously low image. Yeah, 6 mega ohms, that's fine. Mega ohms, yeah, basically no connection between any of these. Which is good by me. That means no explosions. Yeah, basically no connection whatsoever. Yeah. Yeah, it tries to put energy into it to energize it, but then everything doesn't work. All right, well, if I randomly disconnect here, hopefully I'm up. No thanks. Battery and phone's running low. All right, so hopefully nothing explodes. I'm gonna take an earplug off here to make sure. Well, I don't see any fire. Don't feel any fire. Let me take a voltage measurement on this EMS. Hey, 11.4 volts. Perfect. It actually seems to be working. That's awesome. Not cooking my face. Okay, awesome. This actually appeared to work. That is awesome. Okay, we got that. So give ourselves a little bit of stress relief just for the moment. We'll let's put some electrical tape around this. Some stress relief to the wires here. All right. Ideally, we'll heat shrink this or something. We gotta. Let's see if I have any large enough. I don't think I do. No, definitely not. I'd have some other heat shrink tubing to put around this, but yeah. Seems to be working nicely. I'll have to insert that into some of my other projects. Yeah, there we go. We'll just have to do some taps off of here for the the actual 5-volt output, right? But we'll what we could do is put a terminal block on it as well. I don't know how happy things would be with that. Realistically, I want to hook this up to the switch in the robot. Because there is a switch system in the robot here, right? There is a power switch in here, and I'd love to be able to. I'd love to like mount this on the side here for the battery to connect up, and or maybe we move the switch to the other side so that the balance connector does what it's supposed to do. But a couple things we could do anyway. Well, let's cut off this old disgusting connector here. That would give us, me. Is there some kind of JTAG? Yes, there is. So on the Pi Pico, it's these 3 pins. It's called SWD, or serial wire debug. It's rather than having the full 4-pin JTAG test 4 or 5-pin JTAG test harness, you can get away with just a date and a clock pin. The Pico debugger module, which is this thing, plugs in on the center. So we can do that. All right, so we did the BMS. We'll need to put the final outputs on it, but we've got that. We've got really wonder if that battery charger works, but that was BMS, and we've got okay, now so now we could actually start thinking about how to wire up the where we want to put things on here, because since we've tested these components individually for the most part, so all we really have to do is start mounting things up. So the Pico connections are going to be fairly straightforward, just because of what do you call it? I don't know what words I want to use right now. We can even stick this on the back. Look at that. No, it's too funny. Right, we're gonna run this vertically. We're gonna run a terminal block to connect power to it. And we're gonna connect to that'll do the 12-volt there. we're still probably going to have to put 2 holes up on the top here to align the, or to put some kind of bracing connector on there, because we're going to have basically this will screw in near the bottom of the robot, and then we're going to have to punch 2 holes or do something up here to hook up the other stuff. But got that. Sorry, I'm just trying to think where to put the power rails. Well, okay, before we do too much of that, what we should do is do some, like, verify we can control the motors with the Pico or something. Just get some coding out of the way. So I'm going to propose that, alright, I'm going to try to carefully plot this Pico out of this board. Okay, because I'm going to have to charge my phone here again. You have very little battery in the phone. Okay, what I'll do, okay, real quick, we're going to, let's see, is it LiDAR? SWD feels like magic. Oh yeah, sorry. So if you haven't, if you just joined it, let me, yes, LiDAR, we're going to use an old XV11 LiDAR. Okay, I'm about to lose power on my phone. I need to switch back to my desktop and charge my phone here for a second. I will, okay, switching cameras. Okay, but yes, we're going to be using a LiDAR, SWD. Well, thankfully we don't want to do too much of the SWD like ourselves, but anywho, let me switch back. Y'all can't hear me. There we go. There we go. But yes, we're going to be using a LiDAR. I'm going, while the phone's charging, so what we're going to do real quick is I am going to, I'm going to do a couple of things. But while we're sitting here, waiting for the phone, which is the camera, to recharge, the overhead camera, we'll start putting together on a breadboard some of the major functional components of this. So we'll plug in the LiDAR, and we'll plug in the motors, and hopefully some other stuff. Let's see. Okay, so let me, yeah, so I'm gonna start putting some stuff together on a breadboard, and what we'll do is, unfortunately it's gonna be a little, I'll try to talk while I'm working, just to try to keep things interesting, all right, so let me go grab a breadboard real quick, and grab the breadboard real quick. And we're gonna change a couple of, like, we're going to do a lot of things. Okay, so get some new motors. We'll leave the BMS over here. Okay. So a couple of things we're gonna do. Put that over there. Put the Pi over here. Oh, what did I do? Oh, I did that backwards. That's what I did. No.
So I'm just trying to put the cover back on this Raspberry Pi case, and I've completely forgot how this is supposed to work. There we go. Got it. All right. Garbage around. Okay. All the stuff that we're not using. Hopefully get out of my way a little bit here. Turn the webcam back on. All right. Okay. What am I doing? Okay. So, all right. So what we're gonna do, we're gonna put some stuff together on a breadboard. There are two motors in the chassis, but we want to use different motors because we are going to use the brushless gear motors, but the ones in the robot chassis, I believe, are 600 RPM motors, and I'm going to switch them out for 200 RPM motors. But I just need to cut some of these wires down because they're really freaking long, and they don't like staying in breadboards. I don't think they do. Well, actually, no, they stay in breadboards. We'll keep it as is for the moment. We're going to plug the Pico into the breadboard. And what we're going to do, we'll plug, how am I going to power the high voltage devices? We'll go back to the AC supply. So anyway, what we'll do is, this is going to be a fairly simple way of wiring things, just because these motors integrate the speed controller. So we can just do some very simple, oh, yeah, there we go. Theirs are not wanting to stay in the breadboard. Yeah, okay. And the motors don't really like the breadboard too much. The wires are just not high gauge, right? So we'll just line all these up. Plug them in down here. And then it's going to get real wacky because motor wires are long. Okay. Maybe I do what I was planning on doing first. Just shorten the wires. Or maybe we don't. Maybe we wrap the coil of wires up behind the. Maybe I really don't like cutting wires on things I can't replace the wires. So I will. What am I gonna do? I didn't turn off solder here. Okay. What am I gonna do? I'm going to. We'll figure it out. We'll get the breadboard to work. It's fine. We are going to. I really wish I had the desk cam working on this. Okay, so I believe the wiring harness on these motors. If this website doesn't actually say, it'll be really sad. It's basically, I'm trying to think. I think Amazon have a better documentation on this. Hate that. Okay. What color goes to what? Oh, no, come back. What color goes to what? Okay, so ground is black. 12 volts is red. Steering line is white. Speed control is blue. The Hall effect sensor is yellow. Okay. So what we'll do, we'll just start going early. So we're gonna do yellow is GPIO2. Directional control is GPIO1. Speed control is GPIO0. Okay. We're going to define, I'll just put down here, And you can't see because my phone's dead, not on my overhead camera. All right, so we'll do that. We'll then do the same thing for these motors. Of course, the wires are bending opposite directions because it hates me. Okay. I'm missing it. White. There we go. So then we'll just do the same thing that we did for the other one. GPIO3 is the PWM. GPIO4 is the directional, and then GPIO5 is the encoder. Okay. I think we might have set up the balancer a little similarly. Can't quite recall though. Oh, come on. These are really not high gauge wires at all. Okay, cool. How to communicate from Pico to Raspberry Pi? Good question. So, I have got a, let me pull up my other Pico. So, got a Raspberry, if we're looking at the camera, the webcam here. So we've got a Raspberry Pi, and then on the power connector, we've got this USB-C cable, and this USB-C cable will adapt it to a micro USB. Do you treat serial comms as normal UART on the Raspberry Pi? No, we're going to be connecting it via USB. So what we're doing is we're using the Raspberry Pi's power port, because the USB Pi's power port also has USB 2. It's not just power, it does have USB 2. So we're going to configure the USB 2 interface on this power port, and what we're using this cable to adapt it to a micro USB connector, and so the power will actually be supplied via the Pico through this cable. Power and data will go over this cable to the Raspberry Pi from the Pico. And I did test that this works before, and it's a little spooky, but it does in fact work. So that is how we're going to communicate with the Pico. And whoa, yeah, a little funny when I first figured it out too. So okay, so we've got a. So we'll just have to hold my phone in my hand here, but okay. Just make sure I've got this all going the way that I want it to. We've got, okay, so the two motors, they're hooked up in a way. We'll also try to strip some of the code for the balancer to make this work as fast as we can. It's just try to get this up as fast as we can. Let me go grab the grab the programmer and what else do I need? So the programmer, I need to grab a couple little transistory things to drive the Nito LiDAR, and I guess the IMU, but let me see if I've got one more. Yeah, hold on. Let me go dig around my parts bin for a second. Okay. See if I've got a version of the IMU with pins facing downwards so I can breadboard the thing. That might be. I got one where they're the other way around. Because it's on the one in the living room. Okay. Just a second. Never mind. IMU's not important for that, just for now. But what is important is the supply for the motors. Where'd that other wire go? I've lost things. Not lost, but misplaced. Okay. Where did my little black cable go? I've put it somewhere. It was here. It's no longer here. Oh. Okay. Fun. I just gotta find it because I don't want the cats running off with it. You know? Turn off the iron. It's somewhere. Maybe it ended up with the load tester. No, it's not there. What the heck? Where did I put it? Did I bring it over here? No? Oh, I'm at a loss. Okay. Did I freaking do it? Oh, wait, no, I'm looking for a red wire. Huh? Oh! Well, I'm colorblind. No, I'm not, but... Okay. I told myself okay, message retracted. Okay, do you treat serial comms as normally get from the Pi? Whoa, oh, right. So USB to UART, Pico, using Pi serial, so from the Raspberry Pi side. Yeah, okay, so, essentially the way that it works, so Pi serial, yes, but there's no actual hardware, USB to UART, because on the Raspberry Pi Pico, it actually the Pi Pico microcontroller has a USB controller in it. So the default mode for the USB in the Pico is to emulate a USB to UART interface, but it's not. It actually can speak true USB, I should say the Pi Pico does have a USB controller. So while the default is to implement a USB UART that you would then communicate with Pi serial, you could also make the Pi Pico. You could write your own USB interface for the Pi Pico. But yes, for our purposes, we will be using Pi serial. And okay, left my screwdriver. You know what? I got up to grab things. Okay. So screwdriver. Debugger. I need my pile of cables to connect to the Nito LiDAR. Got that. I need a resistor for the collector current. I mean the base current. What did I do with that? Hold on. I'm looking for my little looking for a couple little individual little bits. I got my diode. I need get back in there. Right. Old resistor. Get yes, old Radio Shack. 2N222. Yeah. Old Radio Shack NPN transistors, because that's how we roll. Okay. Alright, so I'll turn the camera back on. Oh, thanks. Yeah, you're very welcome. Okay, so we got 2N4401. Got a bunch of old Jelly Bean transistors we're going to use to implement the drive circuit for the Nito LiDAR motor. Okay, here's a 2N4401, which has a typical gain of 200. Good, 625. Yeah, I don't really know what the difference in the 222 and the 4401. Anyway, base collector. All right, so We're going to connect the... Do that. Yeah, I don't think we're actually going to get things moving tonight. But maybe we can... well, I should say, we will get things moving tonight. What time is it? It's 10. Maybe in the next 2 hours, we can get the... enough code running on the PyPico where maybe I can get the bit of the balancer code that you... Or I can adapt from the balancer code, the code that would let me remote control the balancer. Maybe I'll just get it to drive the motors over here, and then maybe we'll at least write a tiny little PID loop to control the LiDAR motor on the... Well, actually, that would involve knowing how fast the LiDAR is spinning, which we may not get there, but at least get the motors turning, okay? And so we shall connect the transistor, which, looking at it from the bottom, 3 is the collector base emitter, so collector base emitter. So, sorry, I'm looking down. My phone's dead. I'm trying to charge it. It's with the camera, but I'm trying to just. So we want across the okay. So the motor is going to connect here. We're going to need a just back current. Okay. To be how the motor connects. Well, it'll no, that's wrong. Wait, the motor will connect across that, and then hold on. Let me just go. I need real quick. Grab my wiring kit. Okay. Okay. So. We're going to take a bunch of. We're back. I'm sitting down again. Okay. Big old pile of wires here. Get the jumpers that I need. Define. Oh, lovely. Okay. Yellow, black. Well, I don't need any particular color, but it helps to color code things, the colors on the LiDAR itself. So yellow. I want a red. Red. Gonna want do a white for the transmission from the LiDAR. Oh, I tore off another connector. Okay. Yeah. That's motor. And I need one more black for the basically for the ground or the logic side of the LiDAR. Alright, cool. Perfect. Put these wires away. Alright, just so we can. Okay, I gotta actually show what I'm doing here for at least a little bit. Okay, so just so I can finish assembling this real quick, we're almost done with the assembly. Let me flip the camera again. Flip. Yeah, there we go. So basically what we're doing here, we've got a PyPico. We've got these motors, and the reason that I can wire these motors directly into the PyPico is because the motor controller is actually integrated into the back side of these motors. So they're actually a brushless drive. Sorry about that. Okay, I had the phone unmuted. There we go. That should be better. Sorry. Alright, so again, here's what I'm doing. So we've got a Pi Pico. We've got these motors. They're brushless gear motors, and the drive board for these are integrated into the backside of the motor, so we can actually connect the logic. These are logic, inputs into the motor. So we got the blue is the PWM line, the white is the direction control, and the yellow is an encoder signal back from the motor. And the encoder signal back from the motor is actually a 5-volt signal, but the Pi Pico 2 specifically, not the original Pico, but the Pico 2 has 5-volt tolerant inputs. So this is actually safe to do. With the Pico 1, we would have needed level shifters. And then we have to bring in a 12-volt feed into the drive motors. And then over here, we're just quickly constructing just a simple low-side transistor driver, because we actually have to control the motor on the original XV11 LiDAR. We have to drive the motor ourselves. We have to read the RPM signal out of the data stream from the LiDAR and then control the motor ourselves. But that's not too difficult to deal with. So we're just going to do a simple low-side transistor driver here, motor. Low-side, single direction drive. So basically it's just an NPN transistor on the low side. We can switch it on and off. Then the motor will connect across this diode. The diode is to handle the flyback current and such. And it'll take me another couple of minutes to finish constructing this. And I'll just switch back to the other view and then point at this when I'm done. Which is a little more boring than watching me try to put it together. But again, the phone is freaking out. So I'll just unfortunately just deal with this a little bit. But we will record me soldering later when the phone's done charging. We'll just close this AliExpress window. Okay. So let's see here. We're going to connect. Oh dear. Okay. So let's grab we need to connect to the ground to just tie some of these Pico signals here. We'll do the ground over here. And over here. The long ground. Okay, and then we'll just need to do one more of these just to feed the okay. Got that right. Here, let me pull up the Pi Pico pinout. Pi Pico 2 pinout. It's pretty much the same as the Pico 1. Yeah, ground there. Okay. So it's VSys on pin 39. Okay. So that means we can do. So the ground will be. That's the emitter, right? The transistor. Emitter. That's the ground. So we'll do a cross connection here. Nope. There we go. All right. Wire up our plus 12 and minus 12. We're going to do a yellow, I think.
Hey, can you stop eating the robot kittens, please?
Okay. maybe, okay, that wire was too long. Me orange. Yes, orange is good. There we go. Perfect. Almost done. I'm sorry. Okay. Do that. Okay. They're awake now. Oh, I forgot to pull out wires to drive the lighter. Oh no, I didn't. We'll do that. That one. This one. And then we need the data on the LiDAR, which will tie to, where's a UART0RX? So UART0RX, we can use pin 22, which is the GPIO 17. So do that. Bring out actual 5 volts, ground. That'll drive the, okay, then we need one last wire to drive the PWM on the Pico itself. Ground, I squared C1. Alright, it's fine. Do that, bring this over. Ground is, okay, so GP18 we'll use, so that's the 4th pin. Okay, so that one, that one, that one, okay. Okay, cool. Echo. All right, so we've got that wired up. So let's just take a look at this real quick. Select the camera. This cam. All right, so got this wired up. We've got our little low side drive. We've got the Pico. I'm going to quickly just connect some things. These wires really don't want to stay in the breadboard. Or these motor cables, I really need to put some connectors on these. We're going to use a 12 volt supply from AC just to power up the motors real quick. Got that low side drive. We're going to connect that to the LiDAR. We'll hook up our little debugger. So let me just do that real quick. We got the LiDAR pin out. Do negative, positive. Hey you, what are you doing? What are you doing? Hey, no. Okay. Just a second. There we go. Put the wire in there. Let me look at the XV11 pin out. XV11 pin out. Okay. Brown is the, orange is the transmit. Okay. So let me just hook up that to the transmit pin. Oh, come on. Oh, come on. Okay. Oh, nope, we're good. We're good. Sorry. False alarm. Thought I damaged one of my connectors. I did not. I just didn't quite realize what I was looking at. No. Come on. Go in there, please. No, it did work, and then okay, hold on. Yes, there we go. Awesome. Got it. Okay. All right. So now we're just gonna got all of our wiring done. Kittens are still trying to eat the robot. Let me go put the robot away. Okay. Kittens. Hi. You're now up. It's 10 something p.m. and you're awake. Okay. Oh. Sorry. Just crack my back here. Oh. Okay. Turn this stuff around and hopefully not unplug it. Hard, tougher, easier said than done. Oh, they're fighting. Okay, you can see them now. They're all active. Okay. Oh, I gotta connect the debugger. Hold on. Pico. Pin out. Pico. Sorry. I know how this is supposed to plug in. Orange. Okay. Might have got it backwards, who knows? Where's she? Okie doke. So now let's do the good old... Alright. Alright. Code time. So we're going to go into projects. We're going to go into ARM, and we're going to copy the Pico balancer project into the Pico Pico balancer, Pico PyBot. We'll just call it PyBot for now. Pico PyBot. We're going to remove the build folder because that doesn't make any sense anymore, and then change the name of the project to Pico PyBot. PyBot. Any more? Okay, Pico PyBot. Then we're going to vim source/cmake. Time there's a balancer, we're going to call this PyBot. PyBot. Actually, no, we're not. We're going to leave this just balance. I don't want to change all these file names right now. So we're going to disable the UART debug too, and then Pico enable semi-hosting, I think. It's Pico enable. Alright, it's Pico stdio. Wait, no, not the SDK docs. I want the CMake. Yes, that works. Semi-hosted. Yeah, okay, that works. Balancer. That's fine. Okay, so we're gonna do Visual Studio Code. We're gonna close that project, close folder. Pico import project. Change projects ARM PyBot. Everything new. SWD. Enable CMake. Yeah. Sysdap. Enable CMake tools integration. Advanced. Yeah. Import. Okay. We're just going to hack up our balancer logic to just quickly, hopefully all the tools integration stuff works the way it's supposed to. Does it? It did! Use Pico compiler. Perfect. Okay. So we got this. We got deps. We got balancer. Yeah, and we're gonna delete a bunch of this because we don't really need the IMU stuff. We just need, realistically, all we want is well, we'll change how the motors work. Left PWM, left A, yeah, all this is different now. So left PWM 0, left A is 1, there's no left B. Actually, we'll just call this what it is, which is left dir. Right PWM is 3, right dir is 4, there's no right B. So we're going to say left A, left dir, left dir, left dir, delete this one, right dir, right dir, right dir, delete that one, leave that as is, encoder A is 2, and then 3, 4, and then 5. Actually, this is, these aren't quadrature, these are just pulse, so right encoder. So we'll just keep these with. And then we're just going to, we're not going to worry about the encoder setup for now. Oh, sorry. C, not Python. Motor speed, left dir, left dir. All right, we'll do that. It's gonna be 0. We're just hacking up the old balancer code just to make it this right A stuff can just change all, even now that we're right at the end. Doop, doop. Get motor velocity, that's fine. Do that. Motor velocity. False, 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 true. That's fine. PM wrap, PWM set wrap. 5,000. Why did we do 5,000? Oh, because it counts at. I'm trying to figure out the frequency. That's probably fine if it wraps at 5,000 because it's going to be. Hold on, Python. Oh, no, we just need to bring our terminal back. Python. So we have 125,000 or 125 million. Sorry, 1, 2, 3, 1, 2, 3. Like 5,000. It's a 25 kilohertz PWM signal essentially. So it's just completely fine for this. Leave it the way it is. Left, left, right, right. Okay, cool. Motors is good. Packets we'll leave the same because we just want to use the same code for now. Balancer. We don't want to configure an IMU. Although all of our motor control logic was in the IMU, isn't it? Yeah, it basically is. So what we're going to do is motion packet receive next orientation. Well, how did I start all these threads again? Main thread, IMU thread. Only 2 threads, I forget. There's the main task. Oh, there's configuration task, which I think it started somewhere. Oh yeah, it gets started after the network's up. Just gonna make sure our host name is still probably balancer. I think we set the host name to project name. I think that's how it works. Something. Oh yeah, host name Pico PyBot. We'll do that. And then yeah, we don't want to start the IMU task. That's basically what we don't want to do. We just don't want to start up the IMU task. So IMU thread, just comment that out. And then configuration task. If there's a control, what we're going to do is, and then motors. We'll just hack the LiDAR in here for now. Wait, set LiDAR speed. Set motor LiDAR speed. Okay, and then in here, we're going to say motor LiDAR. We made pin 7, oh geez, what did I set it to? I made it 16, 17, pin 18. LiDAR, oh, LiDAR PWM. Motor LiDAR, motor LiDAR. Motor LiDAR speed, motor, we can delete direction. LiDAR. LiDAR. What we're going to do is set the speed, and then once it's up, I'm going to set that to basically 25% because the LiDAR motor typically needs about 3.3 volts, and on a 12-volt source, it's like 30%, 28%, something. 28%, something. Okay, so we'll take the balancer code. Yeah, so what we're gonna do here, we'll say set motor left speed packet dot control dot y, set motor right speed packet dot control dot y. We're going to say plus packet dot control dot left dot x, and then minus packet dot control dot y. Oh, sorry, X. Okay. And then after we power up the motors, we don't want to set up the IMU interrupt because we don't have an IMU interrupt. Motors, we're going to say set motor LiDAR speed at 0.28 F. Okay, theoretically this should still build. I don't think it actually requires us to do anything here. And the control will just sit here and do stuff. So build. I'll take the PyPico. So we'll compile project. Balancer. Oh, oops. Narrowing conversion. So command stopped. Something went wrong. Uh-oh. Pico default lead pin spy. Oh no. Oh. That's what happened. CMake build task is just balancer. There we go. Cool. We actually want to switch to a Pico 2W. Do not use ROS5. Reload window. Uh-oh. Cannot find dependencies. Oh, did my dependencies RTOS kernel? Oh, what have I done wrong? Okay. Pico W Wi-Fi support built. It's very angry at me. Unable to open. I don't want to open croutine. I know I can't open it. Source. CMake lists. Wait, does this not work for... Dependencies, free RTOS. CMake. Yeah, wait a second. There's portable, third party. Free RTOS kernel, portable, third party, community supported ports, GCC. Except I'm not. RP2033, ARM, NTZ. Yeah, add directory, CMake lists. Oh, am I not using a new enough Pico SDK? I'm using 2.1.1. Okay, that's fine. Okay. 2.1.1. Why is this not working? Build project. Oh, it just took it a second. Okay, there we go. Now it worked. It just took it a second. I had to refresh. Okay, awesome. So, in theory, I can install it now. So let me. Yeah. Well. All right. So, need to power this up, and I'm gonna go grab that power supply, and then I need to. I need to power this up. We won't be running with 5 volts. Okay, I need the voltage regulator that I put together. Okay, just a second. Power supply. Okay, just routing the power cable. Goes over there.
Hey, you two. Come on, stop fighting. Stop fighting. Stop being mean to each other. Okay. Okie doke. One last bit. Just gotta... Yeah, let me plug this voltage regulator thing in. Okay. We need a way of running the Pico. Yeah, there we go. Okay. And then do that. And we're going to need to run connection to VBus. I got this flipped around the right way, right? Yeah, out. Minus out plus. Perfect. Watch this not work. Watch this not work at the last second. Oh my god, please. There we go. Ooh. Okay. So we got that. We got our motors all connected. We got our LiDAR connected. I am ready for a power test. Hopefully it does not explode in my face. That would suck. Oh crap, the Pi didn't power up. It's not usually a good sign. Actually, it doesn't have a power light. It only glows if it's officially doing something. But, okay, that's a thing to note. If we then program Flash Project SWD, OpenOCD failed, possibly because I got this connector plugged in backwards. All right. There we go. Hey, it powered up. Nice. Okay. Nice. Okay. So let me bring out this so we can see the LiDAR is now spinning. Can we get any sort of bright dots from the laser? A little bit. Okay. These are not turning because we don't have anything hooked up, but we theoretically, if we switch back to our desk cam, if we're lucky, we'll be able to ping Pico pybot.local. Let's see if the name resolution works. Hopefully this be really nice. Nope, not known, but it can take it a little bit to come up, so I'm not too worried yet. Or did we just call it pybot.local? I can't remember. We called it, yeah, main task, connecting to, yeah, Pico pybot. Enable stuff, host name. DNS work? First try? Never. Okay. Yeah. Okay. It's nice if it does, but you know. X task create. Yeah. All right. Well, I'll keep pinging it for a second and see if it comes up. Let me check my my router here. See if anything came up. DHCP.
Yeah, I don't even... What is that? Expiration... I don't know. Did it connect to anything? Who knows whether it connected to things. Be really cool if it did, but, you know... First try? Never. But, hey, the LiDAR is spinning, which means that the code's up. It just could be very much stuck after that. It could... we don't know if it... how far it got, anyway. Shit. All... interrupts. What else? Where could it be stuck? Where could it be stuck? Well, we do have a debugger, so let's. How do I include error? Let's not output. Well, hey, okay. So if I start it in the debugger, so we flash the project. If I debug. Oh, good God. Right. There's a thing. GDB server session. Wait for the next session. Hold on, let me open this on a different screen just in case it pulls up my Wi-Fi password. Here, so Pico SDK 222. Cogen. Launch, monitor, regs. Where's GDB executable? GDB path. Oh yeah, that's not it. Okay. Debug, where did GDB path? Yeah, because I did do the whole thing. Okay, that is why it's not working. Yeah, GDB path launch. Right, because we got some dumb fucking. Okay, so ls dot pico SDK toolchain. Or rel1 bin or none GDB. Yeah, okay, cool. Okay, cool. Cortex debug. Where is... Yeah, okay. Under program, under executable. Okay, sorry, let me bring this back over here. It's the stupid fucking... I don't know what's wrong with the SDK here sometimes, but we're just doing this because it can't find GDB occasionally, which is stupid, and I don't know why. But nonetheless, it does that. So, GDB path. Okay, so run to entry point. How do I disable that? Run pre-launch task flash. It was... Oh yeah, we just commented out run to entry point because we want it to just keep running. Right. Pico debug. Let's see if we get the semi-hosting. Oh, hey, look at that. Out chars. I don't want to... Okay. Maybe that doesn't work as well as I thought it did. Ideally, what what this does is semi-hosting is it's probably yes, I think is the answer. I don't think it's the SDK. I think it's just the VS Code plugin for the SDK, which is annoying because the plugin is written by Raspberry Pi themselves. So it's a bit dumb. And pure V task waiting. Wait a second. Hold up. Hold up. That don't sound right. Now let's actually see if we get past the arc init. Like, okay, clearly the semi-hosting thing is not fun. So typically what this whole semi-hosting thing is supposed to do is like, oh wait, make the semi-hosting call. What is the semi-hosting interface? So theoretically what semi-hosting will let you do is, like, it'll let you do basically printf through the debugger, so you don't have to eat one of your UARTs or your USB connection. The idea is that you could printf straight through the debugger. But something is not doing what I mean. It's throwing the breakpoint, which is right, but I don't know if the VS Code Raspberry Pi plugin, by Raspberry Pi actually implements semi-hosting print. So we'll just go back to what we were doing before, or I should say, well, let's disable the semi-hosting printf or standard I/O. We'll just we'll just disable all of that, and go back to balancer and run. See if we actually get to our main task here. Oh, we do. Okay. Hey, look. Okay. Static cores, task function, do a thing, yield, continue. We're still running. Okay. I mean, that's what it looks like it's work. I mean, how about we put this down here? How about we put a breakpoint down there instead, and we'll uncomment that one. See if we actually get it. Actually, we could enable the USB debug again and see what happens. Because I could unplug this voltage regulator here and hope that things work. Okay. Failed to connect. Okay. Pi picobot. Well. It's further than I mean, it didn't blow up in our face, so, I mean, we got some things to be happy about. Let's enable USB standard I/O. And we'll flash with SWD. It'll build, it'll flash with SWD. Erase chunk. Alright, verify. Press task to close. Okay, and I'm going to disconnect power just because I need to unplug this regulator if we're going to be powering it ourselves. And I need to do picocom. ACM0. Bad auth. Joining bad auth. Joining bad auth. Oh! Maybe I don't have the Wi-Fi password set up. Okay. Okay, hold up. Pico, Highbot. Trying to figure out what happened. Okay. Ah! Yeah, Kimti. Kimtis are having a bit of a tiff. Oh, yeah, look at that. It erased my Wi-Fi settings from my... when I updated the SDK, or I should say, because there was an SDK update, it overwrote my entire settings file. Great. Thanks, Pico SDK. That's brilliant. Hey, you two. Can you be nice? Now you're having your little fight, but be nice. Come on. Oh. Hey. Hey. Okay, admittedly, the one that's starting shit right now is not usually the one that starts shit, so like I'm kind of tempted to just leave him be. I'm gonna. Ew. That's unfortunate. Okay. Oh, jeez. Popped straight out, didn't it? Okay. Where did it go? Oh, there it is. Another wire didn't quite get in correctly. So do we say orange is the transmit pin off the LiDAR? Yep, there we go. Okay. So, that'll power the 5-volt side. Okay. So, we'll do that. We'll build Bio Project, flash via the SWD debugger. That didn't work. All right, hold on. There it goes. Hey! Okay, so LiDAR is spinning. Let's see, did we get lucky? Ping. Let's see, does it work? Does it work? Oh, wait, I forgot to... Did I... I might have to close and reopen the... Nope, wait a second. I might have to close and reopen the window. Just to reconfigure. I'll close folder. Hi, Picobot. All right. Really? Okay. Flash project. I mean, that's fine. It's not up yet, but it connected to DNS. Look at that. Hey, it's got a DNS, or it's got a DHCP. I don't know why destination host unreachable. That's not cool, but everything else looks good. Let me go grab my DS4 and see if the control works. All right. Connect. Wait a second. Oh, crud. Hold on. How many Bluetooth devices are floating around here? Wireless controller. Great. Oh, there we go. Connected. Nice. All right. Anywho, let's do source.vm and try Python, or sorry, Vim to, or before we do that, tools. Gotta change the balancer. No, balancer client. Yeah, there we go. Balancer, PyBot. And yeah, entering remote control mode. My gamepad. Yeah, there we go. All right, so tools, balancer client. There we go. Oh, right. Dash C. All right. Well, it not doing anything. Damn. Okay. Realistically, that's probably not entirely unexpected given our what we're seeing with our not being able to ping it, or yeah, the fact that we can't ping it should tell us that something's not quite working. I mean, we can ping it, we get an address, but then now we don't even get an address. Okay. Well, if everything just started working the first time, what kind of fun would it be? Okay, so configuration task, send packet, queue receive. It's not like it's not doing something that it's supposed to. Like, no, yeah, it's not like it's not doing something that it's supposed to do. Everything's initialized. What is going wrong? Alright. We sit there and does its thing. Terminal. SSH. Or balancer client. Okay, so it's receiving data. And it's receiving motor control commands. So cool. Oh. Continue. Oh, there we go. Now it's working. Okay, I literally restarted it and then it started working. I don't like when that happens, but hey, okay, whatever, I'll take it. Oh, was my webcam still off? Okay. Let me turn on the desk cam. So yeah, here we are. We're up. I can move the joystick. Motor spin. Oh, sorry, this joystick anyway, sorry. Oh, it's sorry, that's how I have it. So that's forward, and that's the directional control. Yeah, as we can see, the motors are dancing around because they're working. The LiDAR is, in fact, spinning. And next what we need to do is hack up the balancer stuff to actually send the LiDAR data out of the Pico over the network. Or, I mean, that'd be one thing that we can do. But I think we'll probably leave that as our stopping point for tonight. So let's see, so what all did we do? So we went over some design stuff. We just started doing some soldering. We proved that our hardware will work. And so next time, we also evaluated some voltage regulators. So next time, I believe what we'll do is we'll finish the design. We'll finish doing all of the soldering essentially, and we'll hopefully button up the robot so that we can actually drive it around on the ground. And so then the following time we'll start dealing with ROS. But yeah, so I think that's a good point to leave it here for tonight. So for everybody who stuck around, thank you for watching. And I hope you'll have a good night.